shows you something similar. And the stuff that's behind you shows something similar as well. What you can see here is some rocks here which are much darker. If you look at the outcrops behind you, one of the problems here is that there's lichen all over everything. And one of the questions you're asked, now we won't actually mark question 5, but I need to try and give you some guidance on what it was on about, is that you can see folding in these rocks here. And if you look at you've got two distinct types of rock that are just here. Does anyone suggest what they might be? Yeah, so you've got this dark material, which you can actually see fold structures in. And you can see that in the outcrops that are behind you. For those people who can't see this, if you look around behind you, you'll see some fold structures. And within that, there's two distinctly different rock types. So one of them's the structured one. What can you tell me about it? It's quite dark. What are the structures there? I can actually see a bit of sparkling at me on the fresh surface here. Shame to have so much lichen. Someone's shadow's covering up the best bit just there, is that? There's some beautiful folds just here. And some of the layering you can see in those early folds, there's actually quartz veins. So there's quite thin quartz veins that are actually getting folded. And then you've got this coarser grain rock type here. What's that? We'll see more of it up there. We'll see the contact in a bit more detail and a little outcrop up there. What do you think that is? Quite a big grain size to it.
Yeah, bro.
Okay, so there's granitic veins here. And we would have seen something slightly smaller than that back at stock 5. Now, the main body of what's called the tire granodiorite is the other side of the fence there. When we drove through the paddock just before we came through the second grid that was there, you saw these elongated outcrops which are sort of roughly pointing north, but they were sort of basically sticking out of the ground. Granite outcrops are often called whalebacks because they look like breaching whales, a bit like the pair that we saw at Port Macquarie yesterday. So they're called whalebacks. These ones are particularly elongate. Whalebacks in granites are usually sort of like dome-like structures that stick out of the ground. These ones are elongated in a roughly north-south direction, and I'll come back to that. But this granite here is actually a bit different to the granite over there. It's actually, if you look at this, you've got these little pods that are completely enclosed within this metamorphic rock that's here that you can see the folds in. Here I can see the granite that's over there. So a few of the questions that you're asked that we can't really answer here is you're asked how many phases of folding that you can see here. Well, I can see folds, elongate folds that are doing this sort of thing, and their axial plane is running this way. What way is that? North-south. It's 2 o'clock nearly, there's the sun. North is roughly there, so it's not too far off north-south. Okay? And I'll show you something else in the granite just up here in a moment which relates to that. So there's a north-south set of folds. When you describe the orientation of folds, you describe the orientation of the axial plane that's there. Now the other outcrop which we've skipped, there's actually an earlier set of folds which are east-west. And they get refolded by these north-south ones. And if you start to look really carefully, if you look really carefully within the fabric, the main fabric of the rock that's getting folded, you can see even earlier folds, which are isopinal, a bit like the ones we saw on the beach yesterday in Port Macquarie. Unfortunately, this is but here I'll come back to that. These rocks are exceptionally complicated. Originally you might have had bedding like that, isoclinally like this, so you've got parallel limbs, and you can see that on a very fine scale within this layering. Then there was, you can't really see the east-west folds here, but you've got it the other outcrop. Then what's happened is that that's been folded again. So you've actually got a refolded fold, and you can see that in the outcrop here. What we can't really see, there's a little bit of a hint of east-west folds. There's some folds around here you'll see have an east-west axial plane to them, but they're not particularly well developed here. Okay, so they're quite complicated rocks, and that's basically what the question about stock 5 was on about. So that was part of the question. The other part of the question was there's some quite early veins which are made almost entirely of quartz, but down at that stock, a bit like this one here, there's these big pods of granitic material. And the question is, I said before that they're not connected to the main body of granite over there. So how the hell did they get into here? Where have they come from? How did they get there? It's a bit of a trick question. How did they get there? If they weren't injected into there, what's the other option? No, they weren't injected into there.
Flowed.
A lot of people talking at once. Someone's probably saying it right, but then... So it hasn't come in from elsewhere. Yeah, but how? What do you mean transpired? How?
Water,
Almost. Recrystallised via what? What did it crystallise from? Crystallised from it's granitic, so it's crystallised from a melt. How did the melt get there in the first place is what I'm asking. If it didn't come in from outside the rock. Melted from what? Yeah, it's formed right here. Yeah, it's actually formed, it melts from the metamorphic rock. So this rock's got so hot, it's been at higher grade to begin with. So unfortunately we can't really see fresh, we might try and bash up a fresh piece of it in a minute. My hammer, can someone grab my hammer from the other side of the fence? When you look at this, on the fresh surface, it's actually a black rock, this metamorphic rock. It's quite dark, away from the veins. It's quite a dark rock. What would make it dark? Considering it's, well, remember this rock's still the accretionary prism rock, and in fact it's the same rock that we saw at Apsley Falls. But now it's got a black mineral in it. What might the black mineral? And don't say it's not peroxide and it's not hornblende. Yeah, it's biotite. Okay, so these metamorphic rocks now, the rocks that we saw at Apsley Falls, we said they were low grade, right? They were probably only, would have been lower, what they call lower green schist facies, so they probably would have been only 200 to 250 degrees. These ones here, biotite replaces chlorite as you go up grade, and that happens at about 300. These particular rocks have gone well beyond that. They've gone to the point where they're actually starting to melt. Okay, and so they're actually starting to melt, and they're producing, they're sweating out these little pods of granite that are here. Up there you'll see the contact with the main body, but we also would have seen these in stock 5 where we're actually a fair distance from the granite body. So cooked up to quite high temperature, they call that preemptivolite passage, so we're probably 550 plus in terms of temperature. And the question is, one of the questions, the bigger picture question is, what's our tectonic setting again? expecting a subduction accretion complex? Yeah, more detail. In terms of pressure and temperature,
High pressure, low temperature.
you would expect high pressure, low
Low
temperature,
temp.
wouldn't you? Okay. Which is sort of certainly what we saw at the beach yesterday. We saw blue cysts, or the remains thereof. We saw the same sort of thing at Apsley Falls just now. But now we've got relatively low pressure, and we're up to 550. How the hell do you do that? Well, water can certainly carry heat, but there's an explanation that you've just driven across. No, it wasn't the cattle pressure. And it wasn't the cows, it wasn't the electric fence that heated it up either. Although it heated some people up, I heard, on the way through. What's heated it up? The granite. Okay, that's come in from down below. Okay, and there's actually what they call, around the top granite bar, there's actually what they call a regional metamorphic aureole. So the rocks are already fairly hot, so they've come from a little bit further down than the stuff that actually falls. It was fairly shallow. We're probably at around about 12 kilometres down, so around about 3.5 kilobars in terms of pressure here, down to about 12 k's. In a subduction accretion complex, you would expect something like blue cysts at that sort of pressure, but we haven't. We've got quite high-grade rocks. What would you call a rock? Now that you can see individual grains. It's a schist. And the point is that you've got to that high temperature, and you've now got individual grains that you can see, and it actually has got to the point where it's starting to melt. That still leaves us with a problem. We're in an accretionary prism, and we've got a granite. That's the next question. Hey, would you expect a granite in an accretionary prism? You wouldn't. You'd expect it over there in the arc for the week. But all of a sudden now it's here. How do you do that? Yeah, the arc moved. Why did the arc move? Yeah, okay, good. Someone's read the background information. Awesome. So we had that stable arc during the Carboniferous, and during that period this was like a stock standard accretionary prism, like the stuff we saw at Apsley Falls. But right in the latest Carboniferous, slope rollback started to happen, and everything started to unravel and pull apart. When you move the subduction zone back oceanwards, the arc moves with it. All of a sudden, you've got all this heat pumping in to what was an accretionary prism, and then it then becomes the arc. So these granites here actually are a record of oceanward migration of the arc. So we've now got the arc sitting in what was an accretionary prism. Now I don't think you're asked a direct question about that, but it's the big picture thing to think about. Okay. Again, we probably won't mark question 5 because we can't see all the different phases of folding here. And in fact, it's far more complicated than the story I just related, because the folds you see here are actually what they call D3 and D4 and D5. So they're actually later phases of fold. So there's 5 phases of deformation that happen before the granite comes in. So they're exceptionally complicated rocks. In there would be plagioclase, there would be quartz, and the granite boundary actually follows that around. Now, granites when they intrude, when you see at least high level granites, you see them basically cut across all the structures. We describe the styles of intrusion of granites, and we describe things like piston cylinder plutons, and we describe bell jar plutons, where they just cut across existing structures. This one here, the actual granite contact, is actually folding around with the folds. What does that mean? That tells us something. So yes, it means that the contact was folded, yeah. And the other thing you can see is, so these are these same north-south folds that we looked at down there. They're folding around in this sort of fashion, elongate. The axial plane of the folds is cutting straight across the rock. You can see all these rock body directions elongate north-south. Okay, and if you all shuffle past and have a look at this, you can see something else in the granite. There's a foliation in the granite itself. There's a preferred alignment of grains. We actually scrubbed this off last year, so you can see that in a subtle way here. You can actually see that there's a foliation in the granite itself in the same orientation as the main fabric that's in the granite here. It's actually the axial plane. You'll see that the axial plane to these north-south folds projects into the granite and becomes a foliation in the granite. Okay? That comes back to what we were saying before about, okay, we've got this contact and it's following the folds around. You see it cut across the folds in places as well. Just up here it's actually cutting across the layers of folding, but here it's getting folded around with the folds. That sort of says something even more about it. If it's both cutting across and getting folded, what might that suggest about the timing of the intrusion of the granite? Yeah, it's happening at the same time that the folding's happening. Because your schists are starting to fold up, and the granite sort of partly cuts across some of the layering there, and then the boundary itself gets folded. Okay, so the folding isn't like it doesn't happen in an hour. It happens over probably a couple of million years. And during that time, the granites actually come in as well. So you see that the granite contact, you see the schistosity that you see, which is also axial, forms the axial plane of these north-south folds, also projects into the granite. So what I'll do is I'll get you to all shuffle past, but I'll also get you to, I'll upload a photo which demonstrates that up on the blackboard after we get back, okay? And you can have a look at that over the break and try and incorporate that into your report. But try and have a sketch of this again. As I said, it's not designed for 100. We used to have about 50 students max on this field trip. It's not designed for 112 of you, but we'll try and get many of you to actually come and see it as we can. And then as you do that, what I might do is I'll get people to head across, again, go back underneath the fence here in the creek. Don't try and tackle the electric fence over here, as some of you found out it's definitely gone. And we'll have a look at the granite outcrop over near the other fence. We'll have a talk about the composition of the granite. It's getting folded. Where was that, Al? There's two generations of biotite, and I'll come back to that. There's big flakes and there's really fine stuff as well. You've actually got a rock that's very similar to this in the collection back at uni, in your metamorphic rock section. Except this is igneous. Verging on metamorphic. Okay, we'll come back to that in a minute. Okay. Minerals, so we said biotite, what else? Yeah, let's go, there's quartz. The quartz is a little bit hard to pick. It's quite fine grained in here. We'll come back to the deformation in a minute, but when you deform something like a granite, it tends to granulate the quartz, so you get recrystallization of the quartz. So you don't see big rounded phenocrysts of quartz in this thing. What else? Okay, we've got feldspars. We've got both types there, but but they're both white. Nearly all of this is weathered. You'd have to go down a couple of metres to get to really fresh granite here. So all of this has got a bit of a brown staining on the whole rock. But there are two feldspars in here. The bigger ones tend to be the autoclaves. Just like in most of the granites and adamelites that we saw back in the lab, Monzo granite, autoclave tends to be bigger in size, generally speaking, than the plagioclase, and that's true of this as well. But here you've got the problem that they're actually the same colour. If you look closely at some of those bigger ones, you will see simple twinning in them. Okay, it's always a good idea to bring things like hand lenses in the field with you. I can't say I've seen too many this weekend, to tell you the truth. But there are both feldspars in here. Now, you're asked to actually plot this on the Streckheisen diagram. Being it's quite difficult to actually pick the two feldspars apart, let's just try and do a mode, hey? Is there any other minerals present? Have we got hornblende? That's the other thing you might expect in a granite.
Yeah.
Yes has had it there. Who said no? You're right. Okay, there is no hornblende. Okay, that was a trick question. This particular type of granite, you'll never get hornblende in it. It's actually been melted from sediment, so it's actually been melted from a pilitic source rock. Remember, you don't get hornblende in pilitic metamorphic rocks. For the same reason, you don't get hornblende in granites that have been melted from those pilitic metamorphic rocks. So these particular granites have been melted from sediments. Okay, so you won't get hornblende in them. So biotite, we've got the two feldspars, we've got quartz. Anything else? That's probably about it. How much biotite do you think there is? 10%.
40.
Oh, yeah, everyone's overestimating, which is understandable. What you're probably looking at is a surface like that. You're looking at the foliation surface, which has got biotite everywhere. You need to look perpendicular to the foliation. And you see lots and lots and lots of feldspars and quartz. There's probably 10% max of biotite in here.
I said 10.
So when you're trying to do modes on foliated rocks, don't look on a foliation surface. It gives you a biased viewpoint. You need to look perpendicular to that. So 10%, so that leaves us 90% for quartz in the two feldspars. How much of those do you think there are? As we said, the quartz is a bit hard to see because it's been granulated and ground down, but there's probably at least 25 to 30% in here. What's that leave us? That leaves us, say, that takes us up to 40. Let's say there's 30% quartz, 10% biotite. We've got 60% remaining. Any thoughts as to what the ratio of the two feldspars might be? Because they make up the remaining 60%. 2 to 1 which way? What's the Pluton called? It's called the granodiorite. What's the granodiorite dominated by with the two feldspars? It's over the right hand side, yeah. It's 2 to 1 the other way. Okay, so it's probably 2 to 1 plagioclase to autoclase, but again, a bit hard to pick up in hand specimen because they are the same colour and the rock's been deformed. Okay, hopefully most of you have noticed the foliation. It's pretty obvious in these specimens here, and it's obvious in the outcrop. I mentioned before about whalebacks, and they're normally rounded. If you look at the one I'm standing on and the one that Russ is sitting on up there, you can see they're elongated. It's the wrong way, it's this way. That's better. Okay, so, and they look like not the rudder of a boat, what do you call it, the keel. They look like a keel of a boat sticking up out of the, so they're more like a dolphin breaching rather than a whaleback. Okay, so they're a bit narrower, they're elongated, north-south. Where's the foliation in the rock? What's the orientation of that? Yeah, That's why the granite outcrops are elongated in that direction, because the foliation here is vertical and it's roughly north-south. It's same what you saw over there. It's parallel to the axial planes in those folds that we saw. Okay, so all this has happened during or just after granite intrusion. So the granite's been deformed. Is there any other structures you can see in there? What else might you look for? We found a foliation.
There's a lineation.
Okay, where do you look again? This piece on, okay, you look on the foliation surface. So this piece I've got here, the foliation's there. I look on the foliation surface and hey presto, there's a lineation. It's not particularly strong. It's not as strong as the foliation here, but you can see the biotite are strung out along it. And I'll just go back to what I was talking about with the two types of biotite in here. You can see on those surfaces, you can see the big flakes. They're the original igneous biotites that are there. The deformation, what have we had here as well as flattening? We've had shearing happening. The lineation tells us that. And if you look on that foliation surface, you can see there's a whole heap of really fine biotite as well. Now that's been recrystallised as this rock's been shearing. So it's sort of like metamorphic biotite. It's happened at pretty high temperature. This has been pretty hot still when that's happened. But it's had the effect of recrystallising some of the biotite. It's certainly recrystallised the quartz. You can't see phenocrysts of quartz in here anymore for exactly the same reason. It's all been ground down and recrystallised into much finer grained quartz. The feldspars have stayed pretty much intact. If you look on this surface here, when you look into the foliation instead of onto it, if you look in the right orientation, and that happens to be the one that's parallel to the lineation here, you can see shapes like that photo I showed you in one of the lectures. I put up a photo of big orthoclase crystals on a rock that had been sheared, and it had a sigmoidal shape to it, just like the factoids that we saw at Port Macquarie, except this one's not in a basalt or a serpentinite, it's in a granite. And our factoids, in inverted commas, are individual phenocrysts, feldspar phenocrysts from the granite, but they develop that same sigmoidal shape. And you can actually use that. Again, what you do is you get oriented specimens. You can take it back to the lab. This one you can actually work out on the outcrop, and you can actually work out the sense of shear. Now, we said the foliation was north-south. Where do you